So these are the solution for the mean intensity, the flux, and the pressure. Let's relate them now to the equations that we found for the solution of the gray atmosphere. So first, let's take the equation for the pressure. You have that the pressure is related to the flux. Let's call the constant big C. Let me put this here to not confuse that with the little c, which is the speed of light. And use the pressure from the Eddington solution. So we can evaluate this constant of integration big C by the boundary condition. The boundary condition is that at the surface, the optical depth is equal to 0 because the density goes to 0. So applying this equation here to the surface, you can cut the flux term. That means that the constant is equal to the mean intensity at the surface, scaled by 4 pi over 3 times the speed of light. Now, what is the mean intensity at the surface? We have from the Eddington solution that the mean intensity is equal to half of the sum of the intensities. So we can use another boundary condition that at the surface there is no intensity going down. Again, because there is no material emitting, there is only the intensity that is flowing from the interior of the star. So that means that the surface mean intensity, if you can cut this I minus, is simply half of the intensity flowing outwards. And from the flux equation, you know that the flux is constant. That's the first equation, the flux is constant. So if you found what the intensity field is in the surface, you can apply the second equation of the Eddington solution to find out where the flux is anywhere. Because the flux is constant, if you find the flux in one location, you find the flux everywhere. So let's find out what this flux F naught is. You can apply the boundary condition at the surface that I minus equal to 0. So you can write that this F naught is equal to, has to be equal to the flux of the surface, that is equal to simply pi times I plus. So the mean intensity at the surface, you can write this in terms of the flux, that's equal to the flux divided by 2 pi. So that gives you what the constant is. The constant is going to be equal to 2 times the flux over 3 times the sun, over 3 times the light speed. So there you go, we found out what the constant is. Applying this to the equation for the mean intensity, you have 4 pi over 3c times j is equal to the flux times the optical depth over c plus twice the flux over 3c. So we can cut to the speed of light on all sides, extract the flux from this equation. So that's the flux that multiplies tau plus 2/3. Now write the flux as sigma times an effective temperature to the 4th power, which is the flux that is emanating from the surface. So this equation then becomes J is equal to 3 times the Stefan Boltzmann constant over 4 pi times the 4th power of the effective temperature times tau plus 2/3. And because the second equation of the gray atmosphere states that the mean intensity is the source function, we just found our source function. So let's carry on this result. In local thermodynamic equilibrium, according to Fritjof's first law, the source function is a Planckian. Now, if you integrate the Planckian over frequency, you have sigma T4 over pi. Now, this temperature is not the same as the effective temperature. The effective temperature is the temperature that is going to give you the same flux as a black body. This T here, this temperature, is the temperature at different depths. It's varying for the atmosphere. The effective temperature is the temperature of the flux, is the temperature that gives you the flux. So if you substitute this expression for the source function into this expression that we found, you find an equation for the temperature. Now, if you cut the pi and the Stefan Boltzmann constant, this gives you the equation for the temperature as a function of the optical depth in the atmosphere. So this result is shown graphically here. It shows that the temperature is equal to the effective temperature, not at the surface, which is where the optical depth is equal to 0. So this would be the surface here. This is the temperature at the surface. And that's how the temperature increases with optical depth in the atmosphere. It's interesting to see where you'd have the temperature being equal to the effective temperature. You can go back to the equation and solve for the temperature being equal to the effective temperature. That's going to give you tau plus 2/3 is equal to 4/3, 4/3. So that means tau is equal to 2/3. At that depth, the temperature is equal to the effective temperature, which is this line here. That's this location. At tau equal to 2/3, the temperature is equal to the effective temperature. This is interesting. You're measuring the flux. Temperature being equal to the effective temperature means what is the layer that best describes the flux that we're measuring from the sun? And that is not the surface, it's at a depth equal to 2/3. This may sound contradictory at first, since we saw that for an optically thick gas, you only get the emission from the less mean free path. You would imagine then that this less mean free path has the same temperature as the effective temperature that you would ascribe to the flux. But in the sun, that is not the case, and it comes from the fact that in the outer atmosphere of the sun, the mean free path of the photon is comparable to the length scale of the temperature stratification. We saw that the mean free path in the atmosphere of the sun is about 100 miles, 160 kilometers. It turns out that the temperature in the sun is changing on a length scale comparable to that. So within that mean free path that the photons can escape, we are seeing not only a single temperature, but layers in a range of temperatures. The depth of optical depth equal to 2/3 is the average point of the origin of these observed photons. You are getting some photons from a colder layer and some photons from a hotter layer. As you see here from this graph, within optical depth equal to 1, you're getting photons coming from a layer of about like 4,800 Kelvin to a layer of about 6,100 Kelvin. On average, it's as if most photons were coming from a layer of 5,800 Kelvin, which is the effective temperature of the sun. Though this follows from an approximation, the result applies reasonably well to real stars.